One. Okay, we are now recording. All right, we're gonna get started. So I've graded about 33% of your exams. So some of you probably have a grade, some of you don't yet. All right, so I'll be going through the rest. I'm just going alphabetically, so you can figure that out. But yeah, so hopefully in the next couple of days I'll have all of you done. Yeah, so that's the exam. Now we're going to get started with the course today. This is week 7, right? So we're currently on week 7 of the semester, and we're gonna get going. All right, so you guys for section 1. So let's take a look at section 1, table of contents. So we are finished with the large language models sequence. Now we'll come back to it as as we need to, right? Most of what we did in the first 6 weeks, if you notice, was tensor operations actually, right? So obviously that's critical to understanding everything else still. Same operations as before, the matrix multiplication, weights, all that, right? And our focus was language models. We saw our first algorithm, which was just a GPT. At some point, we'll come back to the encoder part of the transformer, which is called the BERT, right? And so we'll take a look at those as well. But it's, if you've mastered the GPT, then BERT is super easy, right? Because it's actually the easier of the two. But we'll come back to that. I don't usually do the translation one, which is the whole transformer, as that doesn't really get used that much, today. But that was the original work. So yeah, so that concludes that first third of the semester. Now we're going to move on to the second third of the semester, which is more regression type problems. So this is going to be, so the motivation here is, there's these AI, right? So you guys are all about AI and everything. But if you notice, AI is really either these large language models, these massive large language models are building these huge data centers for and all that, or it's smaller models that have to do with images, right? And then along there, we also have stable diffusion models, which kind of are a combination of images and also text, because you can write a prompt, but it generates an image, right? So these are, but essentially, if the GPT plays a big role in a lot of these things, right? And you already know a few techniques that we will see when we look at these image models like ResNets and things like that, which are large models as well. So there's that. That's like the AI that you guys are familiar with, right? You hear about Claude, ChatGPT, all that. But essentially, we've covered that already. That's the large language model component. Then there's the other part that actually is where there's a lot of opportunity for you guys, right? You go to a company, you become a consultant, whatever it is, and usually the type of problem that you're going to be dealing with is going to be proprietary, right? It's going to be the data set in that organization, right? And that data set is usually not going to be very large. And I mean, it could be large, like 200,000 samples, a million samples, but at most, right? But in comparison to like a large language model or a GPT, that's very tiny. Do you see what I'm saying? But that's the kind of problem that you might encounter. So, if you guys are familiar with companies, you'll know that in companies, everything is an Excel spreadsheet, right? Or it's going to be, SQL databases, things like that, right? So that kind of data. And so you're going to, a lot of the time, get these problems, right? These problems that, again, your, focus of this course is training from scratch. So you're going to have to build your own models for that kind of problem. And so these are like the regression type problems also, right? So that's going to be the type of problem that we're going to focus on in this second third of the semester. Still using PyTorch and everything, but just more focused on little data sets and all the variations of that. Does that make sense? So the sequence for this, at least today, will be to focus on a few data sets. The iris data set, we'll start with that. We'll do a temperature data set, so predicting Celsius to Fahrenheit, super easy. And we'll do the wine quality data set because, that's a data set that I like because it allows me to use the same data set for both classification and regression problems. So we can actually do this contrast between the two, right, with the exact same data set. Okay, so that's going to be the focus. So we're going to be doing regression along the way. We're going to start covering a few of the other topics, right, like the actual loss functions and things like that. Cross entropy, MSE obviously is the first one for. So we're more into that now. So definitely before in the first third, we spent a lot of time on the architecture, random data. We were not really training, if you remember. We were just doing operations. In this part now, we're going to focus a lot on training. So we're going to be doing a lot of training, and you might get a little bit more homework assignments, right? And then also that reminds me, so as far as the GPT, I know you guys just had the exam, but how is that going? Like, do you guys think you need just one more week or 2 more weeks? That's really all I can give you. I can give you either 1 more week or 2 more weeks to finish that. Pardon? Two more? Yeah, but no more, right? So in 2 weeks, you guys can have it, right? Okay, so I'll set the assignment link then. Is that okay with everyone? No? Yeah? All right, so in about 2 weeks then, we'll do remember, you have to do presentations for that one. You have to come up here and present your GPT, and we're going to ask it some questions and see what happens. Got it? Thoughts, questions? Perfect. All right. So yeah, but going forward, I may give you a few more assignments, given that these are going to be smaller type of assignments, as you will see going forward. And then at some point, we'll cover some algorithm. I haven't decided which one might be appropriate for regression. It might be something like either time series, or it could be neural input optimization. So one of those that relates more to the problem of regression. All right, so the common theme that you should consider is that this is the kind of, as I said, thing that, you'll work somewhere and they'll give you an Excel spreadsheet with 2,000 samples. And they'll be like, build as a model for that. You know what I mean? And it's a very real thing, right? So it's a very real, in companies, they don't share the data, right? So remember, because of privacy, you go to a bank, it's not going to share its data, right? So you don't really have these massive data sets like you do in social media, right? Social media, obviously, Facebook has all the images and all the likes and whatever, right? So there's a massive amount of data. But in this type of problem, just keep in mind, smaller, okay? Got it? All right, so let's take a look. So you guys are section 1. So we've covered all of this already, ML words, tensor operations. As I said, all of this is still very much part of what we're doing. You have your crawler scrape data homework, baby GPT. We've covered that, and I will be updating the link. And then we had the exam 1. So now we're here. This is our first module. So these are your first neural networks, right? That you will be like implementing these. So I'll do a few today. Hopefully, I'll start with iris. I mean, what makes the most sense. That's a classification problem. And, these are going to be either classification or regression problems, but we'll take a look at that. And then there's, other topics like performance metrics we have to evaluate, loss functions, DL losses, batch normalization, differentiation, and stochastic gradient descent, and so on. So we have to cover a lot. So let's click on this one. All right, so I provided some reading materials for you guys. So this is all the materials for you to read for the next 5 or so weeks, this second third of the semester. And the code should be here. So let's take a look. So it's basically of this document that I have provided, chapters 2, 3, and 4. That's what if you notice, chapter 1 was tensor operations, right? So everything that you did, those 107. We also covered the large language model, which would be in section 10. And now we're covering 2, 3, and 4. Okay, so you can click on it, and all the notes are there. right? So start reading through it, okay? And just this is your reading assignment, aligns really well. So all three, 2, 3, and 4. Okay. Obviously this is what I'm going to talk about, but just if you want to follow along. I also provided this PDF version of this. So might be a slightly more refined version of it. I haven't double checked, but this might be a little bit more refined of the same set of chapters 2, 3, and 4. Okay, so read through that. It's the same. So choose to read one or the other, read both. Okay? Questions about that? So that's your reading assignment for the next 5 weeks. All right, and then the code should be here. Okay, so this is most of the code. Yeah, so it's going to be this. So you can see the same thing. I have sections 2, 3, and 4 over here. These are kind of, you don't have to, well, we might come back to some of these. But today I'm going to start with chapter 4. And these are the scripts that we're going to cover. So as you can see, I have several data sets. I have the iris data set and the wine quality data set. Okay. So we're going to go through these and just build our first set of examples. I'll start with iris because it's pretty simple and just build a neural network, right? And go through the whole process, the whole pipeline that you would want to follow, right? On how to build an application. Imagine this is like, you just got this data set, at where you work and so on. And then the wine quality is a more applied use case where they're evaluating, let's say you work for a agriculture company or a wine company, right? And so you want to assess the quality of the wine. And so you want to build a model that predicts for that. And we're going to think about how we can treat this problem using the same data as a regression problem or a classification problem, and just look at how similar they are. About 85% of it is the same, and then there's like a 15% difference. Got it? All right, so I'm going to need, I think I already have Iris, but just in case, I'm going to download these. I'll be using Colab again. So just download Iris. And I'm going to download wine quality. All right, and I will start with probably here. This I think, this is actually Iris. Yeah, so I'll start with this one. Okay. So I downloaded those 2 data sets. I'm going to go to downloads. And there's Iris. And here's wine quality. So I'm going to open up my Google Drive. The Google Drive. Yeah, seems like I don't have them, so I'm going to try to add them. Okay, so I go to downloads. Here we are, wine quality and Iris. Okay. Should be uploaded. Okay, there they are. So I have them now. So now I'm just going to use the Colab environment. say new notebook. Else here. So this is, by no means big data, although sometimes you can build a very big architecture that might require a GPU, but for these data sets, we don't really need anything that big. Okay, so I'm gonna connect to mount the drive. All right, got the drive. I'll start with Iris. There it is, Iris. I'll copy that. Yeah, okay, perfect. All right, and we should be ready then to get started. So a lot of this is going to be essentially, this is like my template of what I always do. Whenever I go, let's say somebody wants me to do something, look at their data somehow, and they give me their data. This is kind of the pipeline that I follow, right? So I load the data, I look at it, I try to assess something about it, and then start from there. I mean, that's the beauty with deep learning, right? So deep learning it's very repetitive. I always equate it to having a toolbox, and you just have like 30 algorithms in there, and you're going to be reusing them a lot of the time, especially with this kind of work, right? You guys know how to use a GPT now, and then might adapt that to some application. But this is the easiest, I mean, relatively speaking, right? The easiest that sometimes just what the problem that you might encounter is that the data that they have is just very noisy or just doesn't work, right? So you just can't learn anything from it. Or sometimes it's pretty easy. That also is the case. So yeah, so in this pipeline, we're going to do this. I'm also going to show you guys how to deploy the models using something called Onyx. All right, so that's kind of like my whole pipeline. Always like they give me some little model, and then the users usually, it's a good idea to not just give them statistics about the model, but actually deploy something that they can play with, right? So they enter in the wine quality, they enter some values, and boom, something comes out. And so that allows them to play with it. And the great thing about it is you can deploy it on your own GitHub. So you can deploy it to the web, and so it makes it, it's inexpensive. All right, so that's going to be our pipeline with this. First homework assignment will probably be something like that. All right, so let's get started then, unless there's any questions. So we're doing the first one from this chapter 4, which is classification, deep learning, PyTorch, Iris. All right, and this is just going to be a classification approach. And then we'll take a look at regression. So here we are. These are the libraries that you would install if you don't have them. MLX10, Onyx. Onyx, as I said, is it's a kind of open framework for deploying models, from PyTorch or other, tool sets or libraries, right? You can use Onyx for deployment. It's very easy. It's just one file. And there's, I think, Onyx and Onyx runtime. So the only thing to watch out for is that these things get updated sometimes, right? So there's you have to specify version 3 or version 7. But I do have some updated versions of this. So if we run into trouble, that should do it. All right. So recover this. All right. So now that we have this, so there's quite a few libraries, right? And usually my pipeline when I do this is always going to be, I start with let's say I'm doing this kind of work, some CSV, got to clean it up somehow, right? Like name conventions, things like that. Then I use pandas pandas data frame environment, and that's for manipulation of the data. You'll see me do that here. Then I usually go from there to NumPy and do a few things in NumPy. And then remember, everything needs to be converted into a torch tensor so that we can build the computational graph and everything like that for PyTorch. Okay, so you can see here I'm using NumPy, Torch, Pandas. I also use sklearn. I like sklearn all the time. I like playing with it, but I don't use it for machine learning. All right, so for machine learning, we're only going to use PyTorch, right? So if I see a homework assignment where you come in with a sklearn random forest, it's going to be an issue. I'll make it very clear, but that's not what I want. Now, I'm not, you know, I don't want to speak badly of sklearn, but the whole point is for you to learn PyTorch. There's only one tool that I will allow you guys to use, which is XGBoost. And only because for this type of data, actually XGBoost is really good, surprisingly good, right? So when it comes to regression type problems, what you might encounter, as I said, I cannot stress this enough. You go to a company or something, it's not LLMs that you're going to be implementing. It's going to be little things like this. And XGBoost is a type of a decision tree machine learning algorithm, not even a neural network one, but it works really well. It's its own library in Python, so we'll definitely do an example of that one. Just because I think it's like almost like an outlier that's really important, even though, yeah. Anyway, so we're going to need sklearn. I'm not using XGBoost here because it's more of a regression tool, although it can do classification. And then our usual torch libraries, which by now you guys should be familiar. And then we're going to take the same approach of the class definition, class inheritance. That's not going to go away. Okay. Torch NN functional that we can use for the loss functions that we need to discuss more now. And Optim, which is actually the machinery that does the optimization. Okay, so let's go ahead and hit run here. All right, so it finished, no problem. Okay, so now let's take a look at the next one. This MLExtend, I like using this library. It's for plotting. So I always do a correlation matrix, always, right? It's very useful matrix. Before all the machine learning happens, I like to see the relationship between the variables, see which ones are positive relationships, which ones are zero, which means there's no relationship, which means that feature is probably really bad, right? So we're going to use that library. So if you don't have it, you'll have to install it. Tensor data sets and data loaders, we're going to continue using that train test split from sklearn. And so, okay. So now, you can see XGBoost is here. Let's actually just try to see if it's available. It is available, at least in my environment, right? So otherwise, you can just install XGBoost. We'll use this a little bit later. Okay, but it did go through. Yeah. All right. So sklearn metrics, as you saw, this is one lecture that we have to do on these metrics and like the math behind them. And especially in this third of the class, this second third, that's something that is going to be pretty, we're going to be using it throughout for classification and regression. What are the metrics? R squared, and so on. All right, so you can see here the confusion matrix also. It's something that we're going to cover. These are all things that provide a lot of information about your problem. And whenever you're trying to, as I said, with a small data set and a small organization, these provide a lot of information, right? So it's a lot of like getting information even before you get the model, or even after you have the model, but they still provide a lot of information. All right, so we've got those libraries. These are the Onyx ones. As I said, I just kind of have all of them. I use like two approaches, Onyx runtime or just the old Onyx, either way. So might as well make sure that you have these for the future. Okay, this one it didn't like Onyx runtime. Oops. XML tools. So yeah, definitely with these homework assignments this semester, the second semester, you guys will be deploying a lot of these to GitHub, so you'll have something that actually does machine learning, right? Um, so that's kind of the plan. I do have a homework in mind already, like a little mini project, I should say, for the end of the semester, besides the homework assignments. All right, so come on. SKL to Onyx. Right. All finished. Okay, let's try it again. All right, finally, right? So we've got all the libraries ready. And so hopefully that you would be able to export a model from PyTorch to become a .onyx model. And that's a file that then you can deploy on GitHub as long as it doesn't exceed, I think the limit on GitHub is 25 megabytes, I want to say. So a lot of these are pretty small. So, but there are tricks actually. There are tricks to, if you have a bigger model, you can deploy it on like even Hugging Face spaces or somewhere else like that that takes, and then from GitHub you can access that. So there are workarounds, but the easiest way is to just do things via uh, GitHub. All right, so that is the libraries, I think, the last of it. All right, so now let's think about parameters. So just the usual ones. You guys know the definition of these now. So epsilon are usually when I have something that's a division by something very small, so I don't have a division by zero error. Number of epochs is going to be like 4,000. So, we can modify it. The learning rate, if you notice, 0.003, can play with that. Batch size, 16. We still load the data in batches. Here in Iris, it doesn't really matter because it's only 150 samples. But say I had 60,000 images or something like that with MNIST, you know, um, that would be important. We will cover also in this second, third, some image stuff, but in the classical way, not CNN. CNN will be the last third of the semester. All right. So yeah, so got some parameters. So all of this pretty easy. Now we're gonna read in our file. Okay. And you can see that I'm gonna use my file that I already copied here. right? The path I'm gonna use, you can see here I'm using pandas. That's what PD is, PD dot read CSV. The path, the delimiter is comma. I believe it's comma separated. And I'm gonna load it into a data frame. This is called a data frame, iris raw data, right? And that's in the format of pandas. I'm not gonna cover pandas in this course. We do have some 400 level courses called visualization, I think, something like that cover these libraries. So they're very versatile, like extremely versatile. You can do a lot. If any of you have taken like SQL, SQL or something, imagine doing SQL type things, but here, you know what I mean? If you've ever heard of that. And so it's definitely very powerful. So I definitely like loading the data into a pandas data frame as part of my workflow because you never know for a specific problem how much processing I have to do to the data. So it's kind of neat to do it in the pandas data frame itself. All right. But yeah, you'll see me use it a few times. Now that I have the data here, I like to look at it. So you can see I'm just going to run it, and you can see I have here my iris data set. So what is iris? I think I've mentioned it before, but let's like formally define it. So this is based on a paper more than 100 years ago, right? So before AI was a thing, this is just some people in either statistics and combination with like botany or something like that, right? They were classifying the iris flower. I think I've talked about this. The iris flower. I think I have it in that PDF. There might be a picture of it. And it's a flower. It's a purple. It can be other colors too. Flower that grows in water environments. And it's become very classic for machine learning because of this data set. So there's 150 samples, which you guys already know. It's a matrix of 150 by 4. The columns are sepal length, sepal width, petal length, petal width. What's great about pandas is that it keeps the labels of the columns in text, but it's nice to have it here, but then you just have to get rid of it when we convert it to NumPy and things like that. But here it's still, you can reference the columns by name, so it's easier in your mind, right? To instead of having to remember it was index 3 or index 7, we can just do things by word, if that makes sense. Okay, you can see the classification. So there's 4 columns, and the 5th one is the class, and this is a classification problem, right? So we're going to say if this is setosa, virginica, or versicolor, right? The 3 types of flower. I am so into this data set that I, at some point in my life, have had flowers of each of these 3 varieties, right? Just because. And if you guys get into machine learning, you can also have that tradition in your own garden. All right. So anyway, so you have sepal length, sepal width, petal length, petal width. You have the data here. You can see that the data is slightly on different scales. These are like kind of closer to 0. These are kind of in the 5 range. Although that's not so significant. What have I said about this? It's always a good idea to do what to this data? Normalize it, right? So normalize it. You can call that scaling, whereas there are 2 techniques, normalization and standardization. And so we will cover this. It's in the notes. All the math should be there, so definitely read through all that. But I will always normalize it because that's always recommended. We're always going to normalize. And so that's going to be part of it. All right, so pretty easy, as you can see. So we can add a few more here. All right, so I have my pandas data frame. And now I'm going to need to convert. So there's a lot of ways of doing this, but this is one example that I have of converting my labels into numbers. So if you guys remember, we're going to build a PyTorch model. PyTorch is not going to accept virginica, versicolor, and all that, right? Strings, so we have to convert it to integers, okay? So that's going to be my approach. I'm just going to use this because I'm using pandas, right? Pandas itself. So then I can just say iris raw data dot species, which I'm referencing the column species dot map. And essentially, I'm going to map the words to these individual numbers by providing this dictionary. Okay? So that then redefines species as having the integers instead of the strings. And you just have to remember how you did it. Okay? So now that it's done, you'll see that the raw data frame in pandas is now, instead of having the words Virginica and so on, has numbers, right? So we've essentially taken a step in our data set. Any questions about that? Pretty easy, right? Super, super easy. So now that I've done that, we can proceed to do the correlation matrix. This is something that I think is essential. You should always do this. Correlation matrix has nothing to do with the model. As you can see, I haven't created a model at all. It's just a statistic technique to look at the relationship between the variables. But it's going to give you a lot of insight. So I'm going to grab first all the columns and their values, and I'm just going to create a list so I can see. So you guys can see that I have 5 columns here. And I'm going to try to compare those values via a correlation matrix. So I'm just going to achieve that by using these 3 lines of code. So I'm going to use from NumPy, I'm going to use correlation coefficient. The first line just takes in the data frame with the list that I've selected. So for instance, notice that I'm providing header list here. So let's say I had 100 columns, right? I can get rid of some of them so that, it's easier, especially at first, maybe you see the whole thing and then you realize, okay, some of these are 0. So the ones that are 0, you just ignore and reduce the size so it becomes much more readable. This is usually what I do when it's something very big. All right, and then once that generates CM, and then CM just gets sent to heat map, which is more for visualization purposes. You're going to provide the number of rows, columns, etc. Okay. All right, there you go. So now I have the correlation matrix, as you can see. So it highlights, it goes from light yellow to dark, purple, right? And so you can see that the key is that the value between variables should not be 0. If it's a high negative value or a high positive value, that's great. It just means that, let's say as my a relationship, like my income goes up, so the number of rooms in my house goes up, right? Something like that, or bathroom. But that's positively correlated. Negatively correlated would be, what's one example of that? The more burgers I eat, the less running I do, or you know what I mean? Something like that. So it's the opposite. So negatively or positively is still very valuable for predicting. Okay, you can see here we got sepal length, sepal width, petal length, petal width, and then we got species, which is this one over here. So species is this one. So I want to compare it to the variables. So you can see that this is minus 61, this is 65, 58. That's species itself, so that's going to be 1. So this one actually, petal length is the one with the highest correlation to the species. Species, of course, being the class that we're trying to predict, right? Independent of whatever model we use, XGBoost, a neural network, Bayesian, whatever technique we want to use, without even looking at a model, we already know. What do I know? I know that this variable petal length is probably the most important. Okay? And then but all of them are important. This one would be the least important at 0.46. So if I absolutely had to drop one, this is where I would start. Do you guys see that? So that's kind of the idea. Okay? And one is negatively correlated. The other one is positively The other three are positively correlated, and that's just the data, right? So you can't fight with this. This is the reality of this data set. All right. Okay. So that's a good first step that you should always pursue, right? Correlation matrix. Okay. So now we've done this part over here. So now the next step is I'm done with pandas. So I'm going to convert this into a NumPy array. All right. So now the pandas data frame to NumPy to create iris raw data NP. You can see that's done there. And now I can just print the NumPy array. And I usually do this. I don't go directly to torch, right? There might be a few steps that I like to do in NumPy, but you can see now I got rid of the column names, okay? And I've got my 1, 2, 3, 4 features, and then I've got the labels 2, 1, and so on. Do you guys see that? And I'm sorry, 0, 1, 2, I should have said. Okay. Seems like it's pretty easy. Okay. Now that that's done, again, I live by the shapes, right? You guys have had a whole 5 weeks to look at this. So I'm going to start printing the shapes, which starts to help me to think about my model architecture. Okay. So here I'm going to print the shape of this NumPy, and it's 150 by 5. I'm going to do some slicing, of course, to separate the X data from the Y data, right? So that becomes a thing that we're going to do. And you can see that here. So remember the word problems, right? How many times I stress the word problems that arrive at X and Y. So once again, you're at X and Y. This is where it's kind of nice because once you put things in this context, then all the code after that usually will work. All right, so here I'm taking the first 4 columns, and this is just the last column for the labels. Okay, so I've got that. And now if you want to look at, for instance, Y, just to make sure that you've got the right column, just double checking on it, you can see I've got my labels there. Okay. Labels here. All right, so that's done. I'm going to change the data type to int. Since these are the labels, they're always going to be int. I can do that. Got it. Well, let's stick. And there you are. So you've got them converted to integer. All right, now this is something that I like to do with my data. I like to see if the data is balanced or imbalanced. What that means is the balance of the classes, right? So in this case, I have 3 classes and 150 samples. Do you guys see that? So I want to know if my data is balanced or imbalanced because that's going to tell me a lot about how difficult this problem is going to be. Okay, so let's try it out. So here I have 3 classes, 0, 1, and 2. So I have these 3 classes, 0, 1, and 2. Okay, so it's going to be a set of size 3. Set of 3. And now I usually like to print a little histogram just so I know for sure that the class balance or imbalance. So that's the other thing of the wine quality data set. It's highly imbalanced, right? So we're going to see how that is going to create problems for us. So here I have a histogram. I create the bins, and I'm just going to plot it essentially. And you can see, what does this tell me? It tells me that there's, class at around 0, around 1, and around 2, which is true. And each one has about 50 samples. Do you see that? Which essentially, it means that the data is balanced. So here with Iris, we know this, but when you get a data set, where you're working or something, this is actually the moment that you're like nervous about, right? So because if it's imbalanced, then you have a problem. So for instance, where might you find a highly imbalanced data set? Well, in a situation where you're trying to build models for fraud detection in a bank. Imagine in a bank, you're trying to detect fraud and have a data set. If the bank is operating well, hopefully more than 98%, 99% of transactions are what? Not fraud, right? And then fraud is actually like a very rare event, but it can happen, hopefully, right? And so that's gonna give you the two classes, fraud, not fraud. It's a highly imbalanced data set. But in here, this is highly balanced. This is very common of academic models, right? Academic data sets. Now, keep in mind, this is done because balanced data sets do better, right? So they're essential. So, if you want to build a model from a highly imbalanced data set, there's an argument to be made for making it balanced somehow, right? But as with everything, there's going to be trade-offs, right? So there's going to be issues to deal with. So yeah, but that's a different problem. Okay, so now I have my two data sets. I'm going to print out the shapes as usual. So that's my X shape and my Y shape. So 150, 4, 150, 1. Okay, I want to see that. This random seed that I do here for the split, I call it a poor person's tenfold cross-validation. And what I mean by that is, instead of implementing a more complex technique like tenfold cross-validation, I just use a random seed. So usually when you're splitting the data, right, by using a random seed, every time that you run this Jupyter, it's going to split the data differently, right? And so when you're training a model, you really shouldn't just rely on like one split. You should try to run this Jupyter 10 times, right? And every time, because it's a random seed, it's going to do a slightly different split of what is training, what is testing. And so that's going to give you, every time that you run it, a different metric. Whatever score you're using, let's say R-square or something like that. What's great about that is then, if you do it 10 times and it tends towards something, then that's the value that you should go with. Do you see what I'm saying? So instead of just running it once and relying on that value, you want to run it multiple times, with different splits of train and test data, and take the average of those results. That's your final one. Because you could get an 82 on one, but then when you run it 9 other times, it's always 69. Or, so really the real one is 69. Because it just depends on how the data was split. All right, so in this case, now if I wanted it fixed, I'm just going to change this from random to just 42, right? So here I'm picking a random number instead of the fixed number like 42 or something like that. If I have a situation where I'm running two models, different models, A and B, then I run on A and I'm comparing to B, then obviously what do you want to do there? You want to have a fixed seed so that you're comparing using the same train set for model A and the same train set for model B, with the same test sets as well. All right, so that's kind of your choice. But for now, I'm not doing that. But yeah, I've had situations where I have to compare two models and my solution is just fix the seed. The seed ensures that I always get the same data set split. All right, so I've got my random there. Now I'm going to use train test split from sklearn, and this will create my data set. So in this type of problem here, we're going to be splitting our data into train and test. And so we're going to use, you can see my split is 20%. So 20% of the data is going to be held out for testing, and 80% of the data will be used for training. So in the case of the iris data set, what that means is I'm using 120 samples for training and 30 samples for testing, all right, to evaluate the performance of the model. This is always good because let's say you're building a model for, for your company or whatever, they gave you this data set, they'll want to know. They'll say like, how well does it perform? So you can tell them then, yeah, well, I trained it on 80% of the data, and when I used the model on the remaining 20%, I got this score. And it could be 30, and that's really bad, or it gets 85, and that's better, right? So that's the idea. All right, so this is kind of how you will present your results. We can print out the shapes here. Print out the shapes. You can see 120 is what I said for training. I have 4 data sets now, X train and Y train, which are obviously going to be used for training, and X test and Y test, which are obviously going to be used for testing. 30 samples, all that for testing. Any questions? All right, great, excellent. Okay, so now, this is an important one. You want to know the data type that you're using. So notice here it says float 64. So this actually, it doesn't matter for iris because it's pretty small. But if we were doing something like a large, architecture, etc., that's a lot of space that's going to be used, right? A lot of RAM, a lot of things like that. And sometimes you could get an error for whatever reason. So what we might want to do is we might want to change the data type to maybe float 32. In some cases, large language models are so big, especially in an embedded situation, that float 32 is just too big. Let's say you want to deploy it on an embedded device. So one technique is called serialization, and essentially, no, sorry, not serialization, quantization. Quantization, and essentially that technique allows you to even make it smaller variables. So instead of float 32, you could go to float 16, float 8. Obviously, you're losing some precision, right? That might be, so it's a trade-off as usual. But the model requires less memory, so it might run faster, and you may find the appropriate balance. Do you guys see that? So that's essentially, these are important things to deal with. So, and I can also look at the data type for Y. The int64 here. All right, we can make some change. I'm going to add a few more. But my point is, we can change the data types if we want. I usually work with float 32. So you'll see me do this in the NumPy still. So I'm just going to take the original X train, Y train, X test, Y test, and I'm going to change the type, notice here, to float 32. I left this as int64, but I wanted to show you the syntax on how it can be changed so you can take a look. And then here, and this is sometimes called np-long. And so it creates the same variables, but now you could call it a bit quantized, right? In the sense that we've changed that to float 32. Everyone with me? Yeah. All right, great. So we can, I've done that. We can check the data type again. That should be now 32. And you can see it does, in fact, say float 32. So you quantized it a little. All right. You're going to be deploying an Onyx model, right? So you'll be quantizing that with whatever you define here. Now we can proceed to do the conversion. So now we're done with NumPy, and we're just going to proceed to create the torch tensor. So we're going to use from torch the function from NumPy. And notice I'm adding these extensions. I'm being very detailed here. So I'm just using tr to indicate torch. I think some people use TH. I don't know. This is what made sense to me. All right, so let's go ahead and continue. So now these are torch tensors. And you can see the next step is going to be this idea of normalization. This is a really important set of steps here. So usually I do the normalization in the model itself. And the reason for that is because people, when they enter their data, they're talking about a blast furnace or whatever, right? They're not going to say 0.03 negative natural gas. You know what I mean? They're going to say 300 kilograms or whatever in natural gas, 32 tons of coal. You know what I mean? So it's going to be in those different dimensions. So you want to do the norm. So you want to allow people to enter the data like that, and then you normalize inside the model itself, right? And so that's kind of like a practice I have. But what you do is you calculate the means and the standard deviations of those data vectors beforehand, and then you just like put it as constants in the model itself. So here I'm just going to calculate them, and I'm going to have them available for later. Okay, so that's essentially what I'm going to do. So as I said, scaling, there's two techniques, normalization and standardization. I usually use standardization, but normalization can be just as good. The difference being normalization is usually a scale from 0 to 1. Standardization is a scale from minus to positive, and it's like -2, let's say, to +2, or something like that. 0 centered around 0. All right, so this is standardization. So you need to calculate the means and the standard deviation. So we're just going to discuss what that means. So if you notice here, I'm taking the X. So obviously, you would not be able to see the test set, right? So you have to assume that you have the train set and the test set. You cannot look at the test set because that's for evaluation. So you can do your normalization on the train set itself. So you need to calculate the mean and the standard deviation of that. So you have 120 samples, 120 by 4, right? And out of that, on a column wise, you're going to calculate the mean. So you end up with a vector of 4, okay, for each. So we can just use from torch tensor the dot mean and the dot standard deviation functions, okay? So we can go ahead and calculate that, and they're done now. So now you're able to always, there's a formula essentially for standardizing your data. So you have the data, whatever the sample is, and you use the mean and the standard deviation to calculate these values. Okay, so I like to look at the data. Looking at the means is always very useful. You never know when you're going to have to like generate synthetic samples or things like that, or samples from the distribution. So this is the yeah, go ahead. The value that because it's the mean across for every column. I don't want the mean of the whole thing. I want the mean of on a per column basis, because every feature is independent, remember? So let's say I have petal length, petal width, and all those. So I have 120 samples of petal length, and I want to know the mean of those 120. And then for sepal length, the same. So if I have 4, you got it now? Yeah. That's how it works, because remember that the variables, it's a good question, right? The variables are independent. So it would be really bad if I'm using the mean across for things that are very different. Got it? Yes, go ahead, please. And in what context? Like, it should be balanced, but how does it relate to this? So this vector mean is coming from the X data, right? So here, if you remember, I had 120 samples, right? And so I'm just taking, there's four. I already don't have the species one because I removed it. So I calculate the mean for the first column, for the second column, third column, and fourth column. I don't count. So I only calculate a vector of means from the train data. I don't do it for the test data. Yeah, because there's technically coming from the same distribution. So essentially, they should have, if I've done, especially because I'm doing this, and actually, your question is good because this is why I was saying do it 10 times, right? With different splits. Do you see that? That's where you actually provided a good example. So you do only do it once and you had like a very weird distribution, right? Then you might have an inconsistency. But by doing 10 splits randomly, you're ensuring that they're all kind of from the same distribution. Do you see that? Yeah. Yeah. And so we really, it's a good idea to do it several times, but yeah, we just need the mean for every column. And from the train set is fine. Because the train set also is 80% to 90% of your data anyway, right? And you're just holding out a little bit, 10% to 20% for evaluation. Good? Perfect. All right, guys, any other questions? All right, great. So yeah, so this is the idea, right? So this is something, as I said, you will always like, I can't think of a situation where you don't want to standardize your data. If you train a model and you don't standardize it, you can always get a little bit more performance by standardizing it. Neural networks in particular really like normalization and scaling and things like that. All right, so I think we were done here. Yeah. So great question. So the means, we'll use this later. We could do the normal. You'll see some people that do the normalizations outside, and that would be fine. But my focus usually in this third is that you can deploy all your models. And so to make it easy, you'll see that we want to do that scaling inside the neural network itself. Okay. All right. So I've got, as you can see, 5, 3, 3, and 1. This is closer to 0, if you remember, and that so it seems correct, right? As far as the means. And so that's my vectors there. We can look at the shape also. It's always good to get a feel for the shapes. 1, 4. All right, so we have that. We want to look at the deviations also, the standard deviations. A few more cells here. Okay, deviations, you can see for X. We don't need to also scale usually for the Y data, although there are situations where this is also desirable, but for a classification, we don't need to. Okay, so these are the standard deviations, as you can see for each of the 4 columns. Okay, and the shape is going to be the same, so I'll ignore that one for now. All right, so I have these 2 vectors. I'm going to use them later, so I'm just going to like save them there for a while, and they can be added later. So now the next step is going to be this approach of creating a data loader. So you always want to use a data loader. And I think in all my examples with the LLM, you saw me use the data loader. Going forward, you will always see me use a data loader. Before data loaders were invented, doing this part was like not fun because you had to do a lot of steps. You had to shuffle the data yourself. You had to get the batches yourself. And it was a lot of lines of code. But by creating your data into a data loader, it does all that for you. Now, the key thing is you just have to learn how to do it. Okay. And if you follow this sort of recipe, you should be able to do it. Okay, always. So this is kind of what I'm going to demo now is kind of the approach. I like to, I have a couple of ways of doing this, but I like to create this list essentially. And you can see that this could apply to anything. Because at the end of the day, whether we're processing images or whatever it is, we can always make it into a vector, right? So let's take a look. So I'm going to create a data loader. Data loader is just a fancy term for the object that holds the data, but in a very smart way so I can like access the data efficiently. Okay. So I'm going to print the shape is 120, the number of rows. I just, confirming that. And then here, this is one nice way of doing this. You just create these two lists of tuples. So a tuple, if you don't know what it is, a tuple in Python is just like an object of two things. A comma B, right? And that's in parentheses, that's a tuple. So here you can see I'm using list comprehensions. And I'm going to do, which we've used these a lot in the LLM. So for I in range, X train shape 0. So that's the 120 samples that we have in the train data set. So I'm going to iterate, and from X train TR, I grab by index. This is just going to add that vector in there, right? Each vector of 4. And then from Y train TR, I grab also the corresponding I, and I make it into an item. So it's not a vector, but just a number. Okay? So you'll see that in a second. So we can print out these, but I just ran it here. So now I've created these lists of tuples where each tuple has a vector and a value, vector and a value. So as long as you can always do that with your data, you then can easily create a data loader. Okay, do you guys see that? All right. So let's take a look over here. So I'm going to, what am I doing here? The exam question 9, I think, of the exam, right? Slicing, right? So you're just slicing this object here. And so you can see I have tuples, right? A tuple, right? Three tuples, I guess, with the actual label 1, 0, 1. And then this is just the vector, which is a tensor of the values. Pretty easy, right? So if you just consistently do things this way, this is going to work. You might be, if you're concerned about images, but images are, square shape, right? So they're matrices. Well, images, when we're using them in this approach, we're going to do something called, that I call spaghettify. So we're going to make them into a vector always, right? Because really, when you want to treat an image as a grid, then you switch to the algorithm of CNNs, right? So convolutional neural networks, et cetera. That's another technique that we will cover later in the semester. Okay. All right. So yeah, like I said, I have an idea for a project that I'm going to give you guys. Kind of excited about that. All right, so let's do this. All right, so now I have my list and I can just proceed to create the data loaders. Okay, so you can see here, I'm going to use torch.utils.data.dataloader, and I'm going to load the iris train list, which is this one. You see that? But notice I'm providing parameters, right? So I'm saying, okay, first of all, I'm defining that everything is a batch of a specific size. So whenever I grab something from this data set, is always batch size, let's say 16. So as you can see, 16 there. So I'm grabbing 16 samples. Do you guys see that? But also it's going to do this thing of shuffling. So shuffling just means like randomizing the data, and that's really good. So that's really helpful, right? So it's going to randomize the data, the vectors, right? When it receives, and you don't have to do it. It does it for you. Okay? And then you create the object train DL, which is now you can reference train DL as a train data loader for your training. Got it? All right. So that's done. And then X test is 30. You guys know this. You can, I don't have to run it. And now I'm going to do the other one, which is torch.utils.data loader iris test list. That's the other one, right? So this one. And batch size and shuffle equal true. So that's really great. Again, we used the data loader when we did the GPT, and we'll use data loader pretty much for the rest of the semester. And I can't stress how nice this is from someone who I didn't have this before. All right, so that's done. Okay, so that's done. You might actually, in the notes, if you read those chapters 2 and 3, some of that I wrote like years ago. So you'll see I was discussing how to do all the, so it was before these data loaders were made available. These libraries have changed a lot. Like I think I told you that the NN linear, right? That didn't exist. You had to hard code those things. This is another example that whenever I see, I'm like, you have it so easy. Because this was not so trivial. All right, so now let's, So you can see that the train DL is actually just an object, almost like a serialized object. When you see these things, it's like a serialized object in PyTorch. Okay, what that means also is it's going to run fast. So that has another benefit, right? It's not your spaghetti code that you're writing, sloppy code. This is really efficient code. So when you have 60,000 samples, or you have something like that, you really want something like this. Okay? All right, so that's done. And we are essentially done with the pre-processing pipeline. And now we are ready to explore some neural network architecture. Okay? So here I'm going to build several architectures. We will later on discuss this in a bit more detail, from linear regression all the way to deep neural networks. But here, today I'm just kind of demoing the full pipeline. So the first, I have a few architectures here. All of this should be pretty familiar to you because we've already done this, right? With the GPT, the baby GPT or the Huck Finn GPT. You can see I have an MLP. I have a DLNet, well, two architectures. And so we're going to discuss them next. So I'm going to grab this one, Neural Network Architectures, the MLP, and what it is. All right. So same things we've discussed before, right? As I said to you, we take this approach of object-oriented programming to define our neural network architectures. We're going to always instantiate our model equal to one of these. So here you can see is the same as before. Class MLPNet, that's the name I'm giving it. We're going to define what MLP means, but it's a multi-layer perceptron. All right, so we'll talk about that. And notice we have the same thing. It inherits NN.module, just like before. What else is common here? It's got the two familiar functions, if you remember, right? If you remember, we had the init class, just like before, and then we had the forward class. Remember that? So same idea. So here you can see that the init class, define, remember these are two underscores. So we use the keyword init. We have this one to initialize the inherited class. And then notice here, we pass two parameters, x means and x deviations. If you remember, this is what we calculated recently for the normalization. Remember that I said that we were going to do this inside the architecture. So we just pass these two parameters. Okay, pass them in. Because it's a class, you want to assign these two variables to internal variables of the class. So we do something like self.x means, self.x deviations. Everyone with me? All right, so that's done. And then I'm going to define, notice we still use NN linear just like before, right? Now I'm going to start adding these functions, sigmoids, the softmax will make an appearance. We need to define these, the dropouts again. So all of this is initialized in this section, right? So I'm going to do self linear 1, self.activation 1, self.linear 2, self.activation 2, and maybe a dropout. This is just where we define these. Notice they all have numbers also. So this is usually better to be defined with a graph. So I'm going to switch to the whiteboard soon, and I'm going to draw, right? So this is where we draw the neural network and tie that drawing of the neural network to what we're coding here. Got it? Any questions? All right. So here we just initialize things, and then here in the forward is where we actually create the inference, right? Everything that we've been doing all semester, taking the X in, going through all the layers to produce an output. So what's happening there? All those transformations, right? The matrix multiplications, remember? X times W plus B equals the next layer, and then that layer times W plus B equal, and so on, right? So that's what we're going to have here. So you can see this is self linear 1. Notice that I also said that there's two approaches to creating this, either NN sequential, right, which we use in part of the LLM, or this part where we give X to a function, it produces an output, that output becomes the input to the next function, and so on, right? So this is the approach that I'm taking here. Got it? All right, so it's 6:17. Okay, so I think let's stop here because it's a good stopping point. Take a 10-minute break until 6:27, and then I'm going to pick up from here, and I'm going to bring up the whiteboard and all that to finish up this example. All right, so I'm going to just end the video here.